out loud, but I'll get right to it then. These images were unveiled by President Biden in 2022. They are the deepest and sharpest images we have of the distant universe. I'm sure you've seen them because when it first came out, this is all that the internet could talk about for a while. And I, like everyone else, was in awe of it. I found it to be beautiful, inspiring, and as an aerospace engineer, I was reminded of the vastness of space and our future in it. These images were taken by NASA's James Webb Telescope that continues to be in space today and continues to take these awe-inducing images. But here's the thing. These images almost did not exist because this spacecraft almost completely failed within just a few months of flight. And that's because it kept getting hit by micrometeoroids, which are a type of small space debris. And these collisions with these objects created permanent damage to the spacecraft, almost completely took it out. And I want you guys to take a second to internally guess how much money NASA spent on building this spacecraft, and therefore how much money would have been lost if this spacecraft failed. I was shocked to find a total of $10 billion could have gone down the drain just due to these small space debris. And this threat to the safety of spacecraft is not unique to James Webb. In fact, every single spacecraft that is in orbit today and will be in the future is constantly under threat of coming into collision with a fatal, or coming into a fatal collision with the debris. And I don't need to stand here and tell you guys about all the amazing utility that space technology offers our lives on Earth right now. And I'm sure that we're all super excited about the future space economy. But that future economy will not arrive if we don't deal with the imminent threat or the existential threat posed to it by space debris. And unfortunately, there is a lot of debris in space, and it is only growing at an exponential rate. As you can imagine, when debris makes a collision with an object, it creates more debris, and more debris creates more collisions, more debris, and the cycle grows exponentially. This is known as Kessler syndrome. And when Kessler first predicted this many decades ago, he stated that if we don't do something about this, then eventually there's going to be too many objects in space. It's going to grow so fast, and there's going to be a point of no return. We can't use space anymore. Now, some would argue we're already past that threshold. There's too much junk in space. There's nothing we can do about it. But I like to take a slightly more optimistic approach and believe that, no, we can do something about it. There is still some time, but we're getting dangerously close to that threshold. So we need to act quickly. And so there's way too many objects. And if we don't deal with Kessler syndrome right now, space will become almost unusable in the near future. And recent events haven't made this easy. Like when Russia blew up one of their own satellites doing an anti-satellite weapons test, it created tons and tons of more debris. So everybody agrees, debris in space is a problem. But it is especially dangerous when you can't even detect it. And that is the case with sub-centimeter sized debris, or what I'm calling small debris. We have ground-based radars and optical methods to detect debris that's bigger than a centimeter or so. But when it's smaller than that, we can't really see it. But like the quote at the bottom here says, we estimate there to be 100 million of these objects, and some of them can create fatal damage. Even a centimeter-sized object like a paint chip traveling at 10 kilometers a second, colliding with one of them is unfortunately equivalent to getting hit by a 550-pound object moving at 60 miles per hour. It could be fatal to your multi-million, million dollar spacecraft. And that's why scientists and engineers have been trying to devise new and clever ways of detecting debris. So IARPA put together this program called Sintra to bring together these people and these ideas to specifically tackle this issue. Sintra stands for Space Debris Identification and Tracking, although I'm not really sure how it stands for that, but let's ignore that for a second. Sintra, in order to tackle this issue, they realized the problem of small space debris is so dire and so complex that when they put out their proposal call, they were willing to accept all sorts of crazy, wacky, and ambitious ideas to solve this issue. And of all of those ideas, there are 3 of them that I want to talk about because these 3 ended up getting funded, and there are people working on them right now. The first of which is to take advantage of the fact that there's a lot of plasma in space. For simplicity's sake, you can think of plasma as a fluid-like medium, but instead of neutral particles moving around, you have charged particles. And when the debris moves through this plasma, it gets charged up. And a charged object moving through a plasma can create interesting waves. More specifically, it can create something called solitons, which are these red waves in the image there. Solitons are interesting because it can propagate ahead of and faster than the debris itself. So the basic idea is, well, we can't see the debris, they're too small. But maybe if we can detect these solitons, then we can therefore detect the debris. So this would be a cool way of tracking / mapping the environment. But this technique also adds an additional feature, which is because the solitons propagate along the direction of the debris, it can theoretically also act as a collision avoidance signal, where if you detect these solitons and you know that the debris is coming towards you, hopefully your spacecraft has enough time to move out of the way. Idea number 2 is to take advantage of the fact that in addition to the plasma, you also have a magnetic field. And when the debris moves across the magnetic field lines, it creates these waves that travel along the magnetic field line called Whistler waves. It's sort of like plucking the string of a magnetic field line and it sends these vibrations. And in theory, we can backtrack these waves to predict the position of the particle that created them. This is a cool idea to map the environment or track the debris, but it doesn't allow for collision avoidance because the waves travel perpendicular to the motion of the debris, so we wouldn't know if it's coming straight towards you. And idea number 3, it comes out of University of Michigan, where they want to take advantage of the fact that because there's so many, hundreds of millions of these objects, and because they have so much energy, when they collide, they release so much energy, a bright flash, sort of like a lightning strike. And if we can detect these lightning flashes, then we can come up with an estimate of the debris density in that area. So this is more for mapping. It's less about tracking because, well, once they collided, you're no longer tracking the same debris. So these are the 3 ideas. The one I want to focus this talk, the attention more so, is for the first idea of solitons because A, I think they're super cool. I think the physics is super rich and holds great potential. But B, because this is what funds me, and therefore this is what I'm talking about. To understand what solitons are, I want to bring attention to this video on the left here of the boat moving through water. It turns out that if the boat travels faster than a special characteristic velocity in the water, then the waves that the boat creates, those waves can detach off of the boat and propagate ahead of and faster than the boat itself. So if you look pretty closely, I don't know how to use this as a pointer, but if you look closely, there are these 2 hump-like structures that are propagated ahead of the boat. Those are solitons. And it's not unique to water. This simulation that I did on the top right here, the red line represents the debris position moving from left to right, and the blue line represents the background plasma. And we see here that as it moves, it creates these perturbations in the plasma that forms into these solitary wave structures that have propagated ahead of and faster than the debris itself. Those are solitons. More specifically, those are called precursor solitons because they're able to propagate ahead of the debris. And this idea was validated experimentally by a team in India where they had plasma flow over a charged wire, and they did in fact detect these solitary structures that propagated in the upstream direction. So that was really cool. From a more fundamental standpoint, what's happening is these are nonlinear waves, and due to their nonlinearity, there's a tendency for it to steepen and grow in amplitude, but they also have a dispersive force that creates a tendency for the waves to disperse and spread apart. And there is a scenario under which these 2 counteracting forces perfectly and beautifully cancel each other out and creates a harmony that allows these waves to propagate over large distances in space and time without distortion to its amplitude, shape, or velocity. There's a famous story of a Scottish engineer in the 1800s named John Scott Russell, who noticed that ships and canals would create these waves, these solitary wave structures that propagated faster than the ship. And he would get on his horse and chase after these for miles and miles and realize, wait, these waves haven't really changed from their original properties. And he was so excited by this phenomenon that he ended up writing about it and became the discoverer of solitons. So the idea for us is as follows, like I already mentioned. We can detect the debris directly, but if we can detect these solitons it creates, we can hopefully, therefore, detect the debris itself. Now, I wanted to keep this talk pretty high level and talk to you guys about the problem of debris and how to solve it. But I would be a bad PhD student if I didn't also show some novel results and talk about some of the contributions we've been able to make to this. So in order to dive deeper into this subject matter and test the feasibility of using solitons as a potential technology, I decided in classic Stanford fashion to do some simulations. On the left here, or there are three main models or ways of modeling a soliton. First, you have analytical models, which I'll talk about in more detail in a bit. Second, you have fluid simulations, which, like I had mentioned earlier, you can think of plasma as a fluid. And so fluid simulations act as a good approximation in many cases. But the gold standard is to use kinetic simulations, where you treat each electron, you treat the species of electrons and ions as individual particles that can be influenced under the motion or under the electric and magnetic field. And so the particle dynamics are taken into account. That would be the best case scenario. But the problem with studying solitons is that because we're interested in propagating these over such long distances and time scales, it would be computationally impractical to try and simulate every single aspect of this. And therefore, analytical models are very important to these studies. And in fact, every single seminal paper written in this field and the bedrock upon which this field has emerged has been done on a couple of analytical models. But nobody has taken the time to test out and understand how good are these analytical models? What are its limitations? So I decided, as a first project in this field, I will try and answer that question. How good are these analytical models? And the easiest and most convenient way to do that is to do a kinetic simulation on a small scale and compare them with the results that the analytical model gives us and see how good they are. So that's what I did. I do that using a technique or a simulation technique called particle in cell, which is a type of kinetic simulation. The basic idea is as follows. You scatter charged particles on a grid, and based on the relative positions of the particles, you can calculate the electric field and magnetic field, and by solving Maxwell's equations, and then using those fields, you push the particles into new positions and new velocities. And then you run the cycle all over again. This is basic. Obviously, it's way more complex than that, but from a very simplistic standpoint, that's what the PIC simulation does. And to compare with the analytical models that I mentioned earlier, there are two classical analytical models to talk about the propagation of solitons. The first being the Korteweg-de Vries equation, and the second, the classic potential method. Here, U and phi represents the electric potential. And so these are the two models I want to compare against. And to do that, I do a 1D particle in cell simulation where I initialize my plasma with a soliton already formed. So I'm not using a debris to create a soliton or anything like that. I start my simulation with a soliton and then just let it run. I'm launching a soliton into a plasma and see what happens and see how good the analytical model is at predicting what I see. So to do that, I perturb the plasma according to the solution of the PD that I just showed, the KdV equation, which is this hyperbolic secant square, and then just launch it. So as a first case, let me see if I can use a mouse here. I'm going to run this video pretty slowly. Okay, never mind. Well, what I want to bring to your attention is this video on the top left here, where you see that the soliton grows and then it sheds off some wakes and then picks a saturated state, after which it propagates for the rest of the simulation. And on the bottom here, what I'm showing is the electron phase space, and we see these vortex-like structures. So that's very fast. We see these vortex-like structures that form, which is indicative of something called electron particle trapping. The electrons keep sloshing back and forth inside the soliton. So that's what's shown over there. And the plot on the right just shows the time history of the soliton amplitude. We see that it grows and saturates at a particular value. And once it saturates at the value, at a shape, I take that shape and compare it with what the analytical models predict. So on the y-axis here is the electric potential, and the way to read this plot is left to right, top to bottom, the initial amplitude increases. And we see that for small amplitudes, the black dotted line is my PIC result, and the other two lines are what the analytical model predicts. We see that for small amplitudes, there's a difference in width. So the shape is not captured by the analytical models for small amplitudes. But when I get to the large amplitudes, the Segdev model seems to predict the width pretty well, but not the KdV model. The KdV model seems to do a poor job across the entire board. Next, when I look at ion density, we see that the height matches, but not the width for small amplitudes. But for large amplitudes, the width matches, but not the height for Segdev model. Again, the KdV model does a poor job across all four of them. Now, basically, what I want you guys to take from this is those two models are not doing a good job predicting the shape of the soliton. At small amplitudes, it seems to vary the width, and at large amplitudes, it seems to vary the height for sig diff. So we asked ourselves, what's going on here? There seems to be some nonlinearity that is not captured in either the sig diff model or the KDV model that seems to affect the shape. And it turns out that both of these are caused by a common culprit, namely the particle trapping that I mentioned earlier. It turns out that when electrons are trapped inside the soliton, it changes the electron density. And that change in electron density was not predicted by those original two equations that I showed you, the KDV and sig diff model. So what we did is we tried to modify that electron density by capturing this new nonlinearity. And we looked at the electron density inside. So what I'm showing here is the y-axis is the electron density. The blue line is the electron density that those original models predicted would be. But we see that that's not the case. The black dotted line is what we're seeing in our simulation. And this pink line is what the electron density as predicted by our new model, what we're calling Schimel's model. So we modified the original equation with this new density, and we find a much better match in shape of the soliton. We were really excited to see this. Now, I don't have time to get into all the details, but we were also able to find some other things, like, for instance, we found that we were able to get a small amplitude approximation of this and find that the shape predicted by our model is a hyperbolic secant to the fourth and not a hyperbolic secant square, and it's a much better fit to the shape. We also find that the velocity of the soliton, which I didn't even talk about, is much better predicted by the new model that we're proposing. And we found some other things too, like there's a cool oscillation frequency that the amplitude is like bouncing up and down at, which matches the same frequency that the electrons are sloshing back and forth. And some other details too. We just published this in the Journal of Physics of Plasma. So if you guys are interested in reading more about this, it can be found there. So to answer the question, how good are the analytical models? Not very good, but we were able to make some improvements. And finally, I also just wanted to quickly showcase some of the other things that we've been doing in this field, which is these waves are only created by charged debris objects. So it's important to model the charging itself. There's a direct correlation between what potential the debris charges to and the kinds of soliton it's able to make. So I created these 3D particle and cell simulations to have plasma flow over the object and see what kinds of potentials it charges up to. And this was benchmarked and hopefully will also soon be published. And on the right here, what I'm showing is a little tool I created to generate random irregular shaped debris objects. A lot of these studies use a spherical model, but very rarely are you going to find spheres as your debris. Like, that's not the case. They have jagged edge shapes and sharp edges, and they're very random and irregular. So this tool here generates these random objects, debris shapes, and then I take the STL files over there, put them into this simulation, and see what kinds of charging happens, what kinds of waves and solitons are created. And so hopefully I've convinced you guys that debris is a major problem, more specifically small debris, and we need new and clever techniques to solve this issue. Solitons is a good leading candidate for this solution, I think. Hopefully, we'll see. We'll take more time to know that. But solitons needs to be understood. The physics is still very open, and there's a lot of questions that need to be answered. And hopefully, my PhD will be trying to answer a lot of these questions by modeling and simulating a lot of these things. Because by understanding solitons, we're hopefully one step closer to understanding its feasibility for the debris solution or the debris problem. And by understanding its feasibility, we're hopefully one step closer to solving the debris problem itself. Thank you.